Okay, so today's lecture will cover some stuff that we didn't finish last time from the general introduction of Python. And then we're going to look at numerical computing using Python and specifically the Numpy toolkit. And finally, look at some of the more basic plotting functions that are available through the Matplotlib toolkit. So we were able to do until did loops at the end for if statements and while statements. So we continue today with one of some other of the more important building blocks of scientific programming, namely functions and subroutines. In Python, you can define functions that contain blocks of code that you want to execute. And functions in Python are defined using the define def keyword, followed by the function name, and then parameters in parentheses or brackets. Functions, as well as if statements, for statements, all end with a colon, because the colon denotes that there is a code block following the line, the function definition. So the next line of a function definition is always indented because that's what the code that belongs to the function. So a typical example here is shown below. Is a define function here, def, and then we have a function called print_doc. We have a parenthesis without any parameters now, so it's an empty parameter list. We still need to specify the parenthesis even if we don't use any parameters. And then you have the colon here that tells the Python that now the following lines will be part of the function. So you also see here that you have an indentation here to the first function that belongs, first row that belongs to the function definitions. So we can run this here. And running this, nothing happens here because what these lines of code do is only to define the function in the Python environment or in the namespace. But once that is done, you can call the function by just specifying the function name and giving a parenthesis here with the parameters. But in this case, we don't have any parameters, so we don't have to do anything more. Just end here and we run this. Now the code that is defined in the function is called. So we can also specify parameters to the function. So in this case here, we have the parameter a here. And unlike many other languages, in Python, we don't specify any data types here. We just pass the variable parameter name in this definition. That tells Python there is one parameter that you have to specify. And then you can use this as a normal variable here in your print function. So what I did here, this str here, this is a function that converts any variable to a string. So that makes sure that whatever I put into my function here, it will print out in some case, because we don't know you can actually call a function in Python with any data type. So that is also one of the dangers of Python, that sometimes you need to check the data types that comes into the function. So now I define that one. And now you can see here that I define a variable b42, and I pass this variable into the function, and I run this. And now you see here that it calls the print statement up here with the and the parameter goes in, it prints out. And you can also see here that the parameter name of defined in the function parameter does not have to be the same as we call the function with. So this is just the variable name you have in the function is a placeholder for the variable reference coming into the function. So in this case, this variable is b, and it goes into the function like this, and it's printed out within the function. I can also, just to illustrate, I can put any data type here. Now b is a floating point value. And if I run this, this will also work. I can actually also print a string. And that will also work. So you can pass anything into a function. So what happens if you want to change a variable inside a function? So here we have the same function again, print value. We have the parameter a, and we print it out here just like before. But what happens if we do like this? We do a equals to 84. So we can run it here. We define the function, and we run the function here. So here we assign b to 42. We call print value b here, and then we print b again. And nothing happened. So this is a feature of Python function here. So all parameters are passed into the function. When you declare or assign the same name inside a function, that will become a new variable that is only visible inside the function. So what happens now is you no longer have access to the incoming variable, and now you have a new variable a that is assigned 84, and it's only available inside a function. So that's why you still have b here is unaffected here. It's not changed at all. If you want to have values coming out of a function, the usual choice in Python is using return values. That is returning a value outside a function and assigning a variable in the function code, just like mathematical functions. So in this case, you have define f here, and we want that's to return sign of x. So you return values out from a function using the return statement. And here then you can assign them here. So if you want to have the value of a function, you assign a variable y here, and that's equal to the function call here. That will call f, and return will assign y the value that it returned. It's also possible to return multiple values. That is very similar to what you can do in MATLAB. So in this case here, I have a test function here, and I return 2 values out to the function, and I specify them as with comma signs here. And this is what is called a tuple as well. So it returns you a tuple, and then you have to assign 2 variables in the after the left side of the equal sign in this case. So let's say if we run this, you see here that pi that should be 1, and then x and y here is the values I assigned here, x divided by 2, 42, and 21. So that seems to be correct. There is, however, one thing to be a bit aware of. So if you have a list, in this case here, a equals to a list of 4 items. Lists are in itself, the values in a list contain references to other data. And it's actually possible when you call a function with a list, it's possible to modify the values in the list, and in that way return values out from the function without a return value. So in this case here, let's see if the list actually has been modified. And you see here, I assigned the first item 42, and you see that 42 is available, is changed in the list that was passed into the function. And that is because variables in Python are references to data in memory, and A here is a reference to a list in memory. And if you pass that into the function, B here will also reference this list here. And B will, if you change the value in that, it will change the value inside the list and assign a new value to the first position of the list. And modify list, so you see here, you can actually modify lists inside a function. If you want to protect from that, there is this notion of using the copy method to actually copy the data to a new variable inside the function so that you don't modify the value. You can also do, for example, a.copy here to make sure that you pass something that is a copy of the existing data. In this case, A is still maintained here. Now it changed. So there is a special method copy that you can use to make sure that data is not modified inside the function. You can do the task. I have too much today, but please take and review this task as well if you have time. So when you have your functions, so you usually define your function to kind of group code that you want to reuse in some way and call in another way. You make code more or less complex by dividing it up in manageable chunks of code. On a higher level, you want to organize all your functions into even more modular containers, so to speak. So, and the main unit of organization in Python is the notion of modules. And modules are used by either using the import statement or the from import statement. There are two versions. And when you import a module, it makes the code from that module available to be called in your own code. So in this case here, I want to import the math functions. I call import math. And then all the function inside math is available to me now. So now I can do math.syn and math.py to access those functions inside that module. Sometimes you don't want to have this. The default when you do this is to have this math.prefix. But you can also, if you want to have a more compact form, for example, using the math library, there is a form that is called from math import star. That will import all the functions that are available in the math module to be directly available in your own code environment. So then the prefix math disappears, and now you can write syn directly and py directly without prefixing from the math library. This is usually not recommended to do because sometimes different modules have the same function names. And if you do this, it will overwrite existing functions. So if you have a syn function that you have defined your own, if you do from math import star, it will overwrite that function without telling you anything. It's okay. So if you want to make sure that you don't have any clashes, the recommended way is using the standard import math statement. That will kind of make sure that you don't have any clashes with different modules. However, the from math import star will import all functions. And sometimes you're only interested in certain functions in a module. Then you can actually specify the functions that you want to import. In this case here, I only want to have the sinus function and the square root function. And that will also work. So this is a way of limiting the amount of work that Python has to do. So if Python does a from math import star, that is significant work to do this import. So if you want more fast and efficient code, you can use the explicitly specify which function you want to import. And the really nice thing with module is that every source file in a Python that you write is a module in itself. So if you write a source code file, that file can be imported as a module as well. So you can have a source code file just containing functions, and you can import them into your own code.
Hello.
Yeah. Hello.
Hey, Jonas, can I ask you a question?
Yes.
Yeah. So you know this math module, like how can you see what's inside there? Like what are the things that it is importing, or choose the things to import?
You can use, there is a, if you have the Spider environment in an interactive Python prompt anywhere, you can use the help function to print the documentation for each of the modules. But I would say the easiest thing is to go into, I can show you here. I can do python.org. There is a documentation here, docs, Python docs. Can you see it?
Yes.
Yeah. And here you have the library reference. This library reference contains all the modules that are available in Python. So you can go to the math module here. And here you have all the functions that are contained in the math module.
Okay.
I think there should be a link to the Python documentation on the Canvas site as well. But this is the way you find out which modules has which functions built into it. And they're also self-documented. So like in MATLAB, you can do help and the function name, and it will print out the documentation for that function.
Okay.
Yep.
Thank you.
No problem. So in this case here, I have written a small module. I put it in a file called prime.py. And this first line here is just a way of telling Python that this source code file will contain international characters. And then I import some other stuff here. I define a function here called isPrime, and which returns the prime number here. So this will be a module, and because I'm running a notebook here now, I have to download this Python file in my work session here now, so I can run it. So I do this. This line here is just to download that file to my session here, so it is available. So now imagine you have a prime.py file in your working directory. Then you can do import prime here. And now nothing happens here, but that is all fine, because what it did now is import all the functions that were available inside prime into my current session. Or it's also sometimes called a namespace. So what I can do now, so now I can actually call my prime function here. So in this case, I call prime is prime3, run it. Yes, it was a prime. And I can call it with another, and it's false. So in this way, you can extremely easily modularize your code. You can collect all functions regarding, for example, a certain part of your program dealing with input-output from file, for example, put that in a module. You can have one part that is only user interface, one that is your computational model. And it becomes more manageable in that sense. Instead of having one single large source code file, you divide it up into several smaller modules. And often a question I get a lot is, in many other languages, there is the notion of a main program, kind of a main function that starts your code. Python doesn't really have that notion. And you can execute any Python file, and it will execute and every statement that there is in the file. But sometimes you want to, because of this duality between modules and source code files, there is a need to kind of specify if you executed a file from the command line or you imported it. So you have to kind of differentiate between those things. So you can simulate some of the the way of doing main file here using a special technique here I'll show you. So in this case here, I modify my module here. I add a single here print statement here that is called that accesses a special variable in Python called _name . And that variable contains the actual name of the current module. So in this case, if I import this module prime here, it will return the name prime. So let's see here. I will download this file here. I call this actually prime extra in this case, so it's a bit different named. And I have a prime main here as well. So if I import my prime extra here, it will print out the name of the module that it's in. So this is way of you can check things if you import it in different ways. But I'm kind of missing one. Yeah. You can also execute this module here. If you, for example, on a command line, if you want to execute a Python file, you type Python and the name of your source code file. You can simulate this in an interactive environment like Notebook using the run statement here. So I run this prime extra.py, and now you can see here that it doesn't really print out the module name anymore. So what it does, it says this is the main script now. So if you execute a Python script from the command line, that script becomes the main script that is executing. And in this way, you can create something that is similar to a main function in Python. So in this case here, I have a main script called prime main.py, which imports the prime module. And then it has a really strange if statement here. So if name equals to main, then it should execute these two commands. If it's not named main, it will not do anything. So in this way, you can create modules that can both be executed from the command line and also imported. So in this case here, if I run prime main, it will say print out the prime values of 6 and 5, but I can also import prime main, and now nothing happens. So using this if statement here, you can create a main function. That is usually when you have your large program, you usually create one starting script file. And in this script file, you have this if name equals to main. So you will see this in a lot of Python code that they do this. It's not strictly required. You can have a main script that does not do this, just print out both of these values directly. But then you get in trouble if you use this module using import. It will also execute these print statements. And if you import a module, you don't want it to be executing code all the time, at least. That was that. You don't have to think too much about it, but it's good to know that if you find a Python open source code and they have a main file, there's usually this if statement that says if name equals to main, then do stuff. And that's similar to the main function in C++, for example. So next, formatting output data. So one important task in many computational codes is that you do a lot of simulation, and you need to kind of write down your data in a way that you can interpret it easily. And the way you kind of make things readable is by formatting your output data in certain ways. There are several ways of doing this in Python, which are multiple ways. You kind of see that there is a lot of different ways of doing things. So I will try to do it by using one of the more later features in Python, which is called .format. So every string in Python has a method called format, and what that method does is it takes the data that you provide to this function, this method here, and it will put it inside a string here. So it will take A, put A in the first position denoted by a curly bracket, and the curly bracket would go away so that the curly bracket will be replaced by the value. It will take B and put it in the next one, and C and do it in the next one here, and D in the final one here. So if you run this example here, you will see it will print out here, and it will use the string as a template for the output. So you can put, if you want to decorate it more, I can have double stars here, double stars here. And if I run it again, the output will also get this here, but it will replace the curly brackets with the numbers you provide in the format statement. This is perhaps not too useful in itself. So you want to be able to control how the output of your format command, your numbers will be as well, and also perhaps the ordering. So perhaps the ordering here is different from the way you want to in the template here. So in this case, you can specify a number here, and that number will denote the order. So number 3 here will go from 0 to 0, 1, 2, 3. So it will put C here, and it will put B in the second here, and the 1 item here in this position. So you can reorder. You can also control the output from this formatting, how you want it to be presented. So for example, I have a Python string here that prints Python 3, and I want it to be printed in a field that is 15 characters wide. So then you can specify the colon here, and then you specify a number inside here that denotes the field width. So if I run this, you can see here it puts the Python string first here, and it fills up the output here with the characters here, so that the entire field here is 15. By default, it's left aligned, but you can change the alignment as well by specifying a greater than sign here, that it should be right aligned. You should look at the direction here that it's pointing to the right, and if you want the text to go to the right, and it will fill up on the left. So in this case, it goes to the right side. You can also do centering. So in this case, you do this French character circumflex and put it before the field width, and it will center the text. So now it tries to pad both sides here so that the text should be reasonably centered in the middle. It's also possible to denote the character you want to use to fill the space. So in this case here, there is a underscore character before the centering, and then it will use that character to fill up the blank spaces here. Most of the common things you want to do with formatting is formatting numbers of different kinds. So controlling the output of the floating point or integers in a way that it looks nice in tables. And what you have to do first is to tell this formatting string what kind of data type is coming in. So in this case here, integers has the character D. So D stands for integers in the formatting strings. For integers, it doesn't matter too much how you can, they're always kind of presented the same way. But you can use the same field width and controlling if the number should go on the left or right side here. So here I just have all the same examples that I did before for strings, but for integers instead. So now you can see that the numbers can be centered and it can be left aligned, right aligned, and so on. And by default, numbers are always right aligned. You can see here. So if you don't specify any alignment, it will put the number on the right side in the field. Then we come to the more important thing is how you format floating point values. So there is a special placeholder called F, which you can use to format a floating point. And you can then you specify the field width and the number of decimal points you want to use. So in this case, the field should be 10 characters and there should be 2 decimals at least. So let's see here. Yes, you have the field width is this part here. And then this is the 2 here. So 2 decimal points, decimal places. And then we have 4, that's also correct. And we have 6. Then you can also do scientific notation using the E placeholder. It works in principle the same. It's just that you specify, it's also the decimal places you specify here. Otherwise, it will report in the scientific notation here, using the number of decimal places you want to have in your output.
Can I ask a quick question?
Yes. Yeah. So if it's not big enough, we can try it out. So if you specify a smaller field here, it will fill out. So it if it doesn't really small here, just see. It will ignore it. So it in Fortran, for example, if you specify fields, it will use stars to kind of say that this field length is too short, and I don't want to print it. But this will just ignore it, and so you have to make sure that you have enough space if you want to have columns correctly. Another cool thing is that you can actually also name these placeholders. So in this case here, I can do in my template string here, I have parentheses and I have curly brackets X and Y. And then you can specify the variable names directly in your format statement, and the variable names will be used for the replacement here. So then you can basically just format it in any way and then just send over the variables to the format function. It will automatically substitute the correct variable name into the print statement. So in this case, it will print out coordinates, for example, here, and it will use X from the first parameter, Y from the second parameter. An even more cool feature is that you can use dictionaries as input here. So I have a dictionary here with value pairs here. So value 1, 42, value 2, 3.4, and value 3, Python here. And I can specify the names here in my the key values in the format string, and then I can just send over the parameters using a special notation here, $params. I really don't know why Python does this, but you have to do it if you want to send it over. So *params, and it will replace the correct keys with the values here in the output. That is really cool. And the final really cool feature is you actually don't have to specify any variables in the format. You can use, there is a special function called globals in Python. And global is a dictionary of all the variables you have created in your Python namespace or session. So it's similar to MATLAB. There is also a function that can vars that prints all the variables in Python. So in Python, all the variables are stored in a dictionary. So what you could do is you can have a print statement here with a formatting string like this, and you can define your variables just like normal variables in your code, and then you pass the globals functions over to the format statement. And then the format statement will pick any variables in the namespace and replace them here in the print statement. So that's cool.
How do you combine this with the formatting that you had before with the columns and like the number of?
Yeah, and then so the name is on the left side, and then you have colon, and then the field width. So like this, and then you have D or something. So it's just a way of naming, and then you after the colon you specify the formatting.
Thanks.
Yeah. Also, the final part of this introduction to Python is handling files. So when you have a computational code, it usually has to write its results to an output file. It perhaps also have to read the input from a file. And in Python, opening files is done through the open statement. So it's a function that takes a file name as input, and you can specify if you want to read it or write to a file. And it returns you a special file object that you will use to kind of write to these files further along. So basically, it makes a connection with a physical file on your hard drive, or something that will be created later on, and an object which you can use to write to this file. So in this case, to write to a file, the first thing we do is create a text file object using the open statement, and the first parameter is the file name. And Python will always look by default for files in the same directory as your source code. So in this case, it will look in the current working directory of your executing code. And then it will, second parameter here is specify what you want to do with a file. So a single string here with a W, that means write to a file. And that will, if there is an existing file, it will overwrite that file. So just think about that. There is way of adding things as well, but I'll come to that. So I open the file, and now I have a text file object here that is available for me to use to provide input to this file. And that is done using the .write method, which is provided on this object that you get. And then you call write multiple times, and it's not the same thing using the print statement in Python. We always print and do a line carriage by default. The write statement will write just the strings that you provide to it. If you want a new line in your file, you need to specify a \n in your write statement. Otherwise, it will continue on the same row indefinitely. So in this case here, it will write filens innehåll, and then we'll continue to write on the same row, detta skrivs på samma rad. There is a \n, which will denote it sends a new line. It will go to the next line, and then it writes this text on the next line. So these three statements will create 2 rows. And then when you are done with your file, it's very important to actually tell the operating system that I'm done with this file, because all operating systems have a lot of routines for optimizing file I/O or writing to disk, because it's a very not complex, but it's a long running task. So it can take some time to write to disk. So that it tries to keep the things that are being written to the file in memory as long as possible. And at a certain point, when your computer is not working too much, it writes down to disk. And so it's important when you're not using the file anymore, I'm done with it, you have to call close. So there's a method called close that will close the file, make sure the data is being written to the file, and finishes off. So then we close the file here, and then we can look at the file. Well, what did we create now? So what I do now here is I execute the system command in this notebook here to list the contents of my file. Now you see here that you have only 2 rows. These are the same row. Then I had a new line character here, and then I continue on the next line here like this. So reading from a file is very similar to actually writing a file. It's just kind of opposite way. The difference is that you specify R in the second parameter of the open statement, and then you use read to read things into the file. So in this way here, I open the file that I previously wrote, and then I can read the entire file in a single line if I want. So there is a read statement here that will return the entire file as a string. And then I close my file here and I print the content. So this is perhaps a really dangerous way of, if you have files that are gigabytes in size, it's not a very good idea to read the entire file into string in Python. So that we need to kind of deal with that in different way than just reading everything in one go. So instead of reading everything in one go, there are multiple methods you can use. One of the more common one, for example, if you're dealing with text file, is using the read line statement. So in this case here, I open the same file again, and then there's a method called read line, and that will read one line of your file and return that as a string. And if it returns empty, it's at the end of the file here. So I have a while statement here. If line is not empty, continue to print out the line and then read the next line. Then I close my file again. So in this case, you can see here that you get the first row, the second row. And then we have the strange thing. Why did it print out a different line here? And the reason for that is that read line reads everything. It reads also the carriage return and includes that in the string that it reads in. So when I print out line here, it will actually print out an extra new line as well. So print will add a new line and line will add a new line out. So we get 2 lines here. So that's something we have to solve. Yesterday I told you that there is a special command for doing the cleaning up strings. So this is a perfect opportunity to use the strip commands to remove unnecessary stuff. So in this case, we know that we have an additional character at the end, the new line character. So we can call write strip, and that will remove the new line character from the string. And now the output should be more similar. So now you see here it prints out 2 lines here of the created file, which is correct. And also we add R strip on the read line statement inside the while loop as well. There are multiple ways of actually reading from a file in Python, which is kind of nice. So we can treat the file as we are looping over a variable as well. So in this case here, I open my text file for reading, and then I use the for statement here, for line in text file. And then I can just print line R strip here. So it will read one line, and when you have done the code block, it will read the next line, which is kind of very Python-like. Same syntax is used for normal lists, you can use for files as well. So it will also output the same thing. And there is also a very nice convenient function called read lines, which actually will read every line in the file and return a list of lines. So in this case here, it will take the text file, read all the lines, and return a list of lines. So you can see here you have the first item in the list is the first row, and the second one is the second row. then you can loop over that list later on to process it in different ways. That is also something to be a bit careful when you do, if you have large files. For really large text files, it's better to read line by line, do processing, and then continue reading. This will allocate memory for the entire file in your computer, which could be limited. So that you have to think about. There is also another nice thing you can do when you have reading, because you want to ensure that you call close on your file. And sometimes that can be hard to do. So there is a new statement called with in Python that
I think someone asked a question.
Oh, sorry. Yeah.
In the chat.
Yeah. So I can see. So where does the file end up when you write them? So if in a notebook, the files end up in the current directory of the notebook. So if you look at the file here, you can see on the left side here, there's a filer, and it creates it in this directory. So that is the working directory of the notebook. If you're running standalone, the files will be created in your working directory. So where you executed your Python code from, there it will also write the files, if you don't specify any search path in your directory. If you want to specify a certain directory where you want to read and write, you can specify here using so home UNAS, for example. Specify a search path here in your open statement. So that is the way you can control the output of the where you want to write and read files as well. I hope that answered your question. Yeah. So the with statement here, what it does is it works on objects that return something that opens or closes things. So it opens this file as text file. So it's basically the same thing as assigning a text file object. And then you do lines and you do your read operations, but you don't have to do the close. So close will automatically be handled by the with statement. So it will ensure that close will always be called, regardless of anything. So in this case, even if the file there is something wrong, it will close the file. So this is the recommended way of opening files in Python, is using the with statement. So that is and that can also work on other. For example, if you're opening a web page on the internet, you can use the with statement to make sure that you close the connection, for example. So it works on many different objects that have a close method. So welcome back. So the second part here will be on numerical computing with Python. So we have already in the previous lectures gone through how Python has very flexible lists and dictionaries and data structures for handling generic data. However, you should never use lists and dictionaries for large matrix-like structures or arrays in different ways, because lists and dictionary are designed for different things. They're designed to handle different kind of data, data types in the same data structure. If you want to process numbers, arrays of numbers, you should use a different data type instead, and that's where Numpy comes in. So Numpy was developed from a numerical kit called Numeric, and then it was called NumArray, and then finally multiple libraries decided to go together and standardize and create something called Numpy. So Numpy is an extension to Python, which is provided as several modules, but those modules are implemented in C and are very highly efficient in doing array computation. So Numpy provides you with data types for vectors and matrices and arrays that can be manipulated with very high performance, and you can do matrix and array operations with high performance. So using Numpy is fairly simple. The standard convention of importing Numpy is using this statement. So import Numpy as NP, and this is a way of instead of having to prefix every function of Numpy with Numpy, you instead use NP. So it's a short form, and it avoids the clashing of using from instead. So NP is quite easy to use. So that's why in the rest of the examples here, every time there is an NP dot, that is the same thing as short form of NumPy. The main data object in Python, in NumPy, is the array object. And that is kind of a main data type. And it can handle multiple arrays with different dimensions. And the special thing with these is that they are often allocated as large chunks of memory in your computer. So, so the numbers is very close to each other in a single block of memory. That makes it much more efficient than having multiple blocks of memory that you usually have, for example, in C, C++, or in Python lists. So in this case, you will have a very efficient array in memory that you can access really fast. You create, I have to run this command as well first. So you create arrays, array objects using the array function. One of the ways of doing it. And in this case, you specify np.array, which is the short form for numpy.array. And then you can specify as the first parameter the values of your array. And then here you see something that is a bit different from the normal NumPy, is that you actually specify data type. So an array always has to have a certain kind of data type, and every number in the array will have the same data type. So in this case, even if I specify 3 integers, the array will be a floating point array. So you will see here that there are decimal points here of each of the values in the array. And if no data type is specified in the call, NumPy will try to determine the data type depending on the data you provided in the parameter. So in this case here, if I provide 3 integers, the array will also be an integer array. So the data type of the entire array now is integer. If you specify floating point as input, the array will be floating point. So as compared to list, arrays can only contain one single data type. You can specify multidimensional arrays as well. So in this case, you do nested lists here. And then, so the first internal list, that is the first row, this is the second row. And you can hear, in this case here, there is a array with 2 rows and 4 columns. So this is the first row, this is the second row. And here I also specify that it should be a floating point. So here, when you print them out, it prints them out in this format here. So they actually, it's similar to what you do in Matlab when you print arrays. It will print like actual dimension of the array when you print them out. So as I said before, arrays are stored in blocks of memory, blocks of values in memory. And the notion of dimensions in array is just a way of getting to different points in a single one-dimensional block, because the data that you created for an array is always stored as a one-dimensional array in memory in your computer, because operating systems only understand the one-dimensional chunks of memory. So there are a starting address, end address, and everything between there is floating points. So if you look at how NumPy stores arrays, so in this case here, I have an array A, and the shape is, it has 6 rows and 5 columns. And you see here that the values are stored row-wise. So you see here 1, 3, 7, 9, 0, and then it starts on the second row, 2, 5, 3, 8, 4, and so on. So it's stored in this way in memory. And if you have programmed Fortran, Fortran does it in the opposite way. So Fortran stores it column-wise. It goes down in this way. So by default, NumPy uses the C way of storing arrays. It's called row-wise. And the Fortran stores it column-wise. It's column by column. There are ways of creating arrays in Numpy that are using the Fortran storage array, and that is important later on when we want to communicate with Fortran codes, is that we create arrays in a way that Fortran can read them directly. So if you pass a C array to Fortran, the dimensions will be reversed. So that's why it's important that you can create arrays that fit with Fortran as well. So if you have arrays, you can query the information on the shape of the arrays and other information on the array. There is a attribute called shape, which provides you with the different dimensions, how many rows and columns you have in your arrays. So in this case here, a single one-dimensional array, the shape is 4 comma. So it always tuple with 2. If there is no, if it's a one-dimensional, the second is left. Second item is left out. You have a 2 by 2 array here. The shape is 2 by 2, and then you can have actually how many dimensions you want in an array. So in this case here, there is a 3-dimensional array here with 2 by 2 by 4. So you can have any dimension. So an array is not a matrix in that sense. So it doesn't know anything about matrix operations. It's a generic way of storing values in different in memory. You can also use shape to assign variables, or for example, the number of rows and columns very easily. So you can do r comma c here, row column equals to shape. So r then will become the number of rows in the array, c will be the number of columns in the array. You can also query the dimensions of an array using the ndim property here, .ndim. So in B will be 2 dimensions. And there are a lot of.
We have another question.
Yep. Is the question that on the indentation? So with which code was that? Okay. Do you mean here? The indentation of these? That is not important. It's just for readability. So you can also query a lot of other things. So shape, ending, we already covered. You can query the data type of an array by using the dtype attribute. You can return the number of elements, the total number of elements in the array. You can also query how large each item is. So for example, a floating point usually in Python is stored using 8 bytes, and then item size will be 8. If it's an integer, it should be 4. So let's see what happens here. Okay, it's longer integer. Okay. So in this case, there are 4 items here. So the size is 4. You can see here that there is a data type called int64, and that is 64 bits of integers. So in this case, it's 8 by 8. So that's why it's 8 here. So each item in the array is stored using 8 bits. No, 8 bytes, sorry. So that is also some, if you process arrays, you can query what the array shaped, or you can query the sizes of them and stuff like that. And the size and item size can be important if you write them to disk later on. So the shape of the array can actually be changed. So Numpy goes to extreme long lengths to try to avoid reallocation of memory, because that if you have large data structures, that is a heavy operation to do. So if you want to resize something and it's less elements or more, it has to kind of delete the existing structure and recreate it again. And that is extremely inefficient. So I have created you don't have to know the details. So this is a function that returns the memory address of a certain array in memory. So we will try to reshape an array and see what happens to the actual memory location. So in this case here, I create an array 2 by 2. I print it out and I print the memory location of A, and then I reshape it to be flat. So reshape function will can be used to reshape an array. As long as you don't change the number of elements, you can use the reshape. And then we print out the memory here again and see what happens. So you can see here that the 2 by 2 And the memory location here is kind of a really large number in my memory in my computer, but it's ends 304. We reshape it, and you see the memory location doesn't change. So reshape is a operation you can do without any computational costs, not very small computational costs. So the array, the dimension is a construct. And also, if you look here, A flat and Numpy also tries to reuse the memory locations as much as possible. So if you create A flat, that is a reshape. That A flat would actually refer to the same memory as A. So there is no copying here. This is just kind of a different way of referencing A. So if we, for example, change A row column 0 here, so this is a way of, so accessing arrays is done by using square brackets, and then the first one is the rows, and the second one is the column. And then I assign that value 42, and then we print it out and see how both of this structure looks like. So you can see here, 42 is available in A, but it's also available now assigned to A flat. So both of these points to the same memory location, but it's viewed in two different shapes. So again, I mentioned it before, if you don't want this to happen, you can do a copy. And then you explicitly say that C equals to A copy, and then you assign C 00 here, 84. And then I print out C, and now we will see a different result here. So now you see here that C is actually at another memory location than A. So the dot copy here, you can actually make a copy. That can, of course, be a costly operation depending on the size of A, but this makes sure that you don't share data between the references.
This memory of thing and then the 943, is this the pointer, or does this somehow contain the information within the array, or?
The memory of that function actually returns the pointer in memory.
Right, okay.
But it can also, you have to use a bit careful because Numpy is a bit, I would say, magical. It does a lot of things to save operations. Sometimes you can get a memory location that is offset a bit because it references a bit inside existing allocated memory. So, but most of the time it's the actual memory location of a certain point. But usually you never go. This is just a special thing. You can see the memory function here is a bit odd. So it goes a bit deep into data structure. Usually you never go to that depth to kind of modify your data. It's just a way of illustrating that something hasn't changed in memory. Let's see here. Yes, copy. So some other example here. We have a B array here, which 2 rows. And then you can reshape it to make it completely flat. You can make it in different ways. So as long as they are not, the number of elements is not changed, this will be valid as well. However, this is not the same thing as doing a matrix transpose. If you want to transpose of an array, you can use the transpose function instead. So there is a special function called transpose here. So this is the transpose of the array B. These are not the transpose. So just a note. So if you want to change the actual size of the array, there is a resize method, and resize actually reallocates the object. So in this case, if you allocate a 2-dimensional array, you can resize base here to be 9 by 9 and 4 by 4. And then it will actually take the values of the existing array and fill the new array with those values. So in this case, you can see here that 1, 2, 3, 4, and then it will just kind of take these values and repeat them for the entire array. So in many of these examples here, I've been a bit for small arrays, but usually you are dealing with large arrays, and you can't create them using a single array function. You need some functions to be able to create zero arrays or arrays with ones in them, for example. And this is very similar to what you do in MATLAB. So they model a lot of the functions on what you can do in MATLAB. So if you want to create an array with zeros with a size 4 by 4, you can do np.zeros, and then you specify the dimensions, and then you get a 4 by 4 zero matrix. And the same thing as for array, you can specify a data type to make. If you want an integer array, you can specify int here. If you want a floating point, you can specify float, but floating point is the default data type. So in this case here, this is the same thing as specifying like this. There is also similar method called ones that will create arrays with ones in them as well. Same syntax here. You can use floating point or not. And you can use ones actually to, if you want an array with a certain number, you can use ones to actually first create an array with ones, and then you multiply it using a scalar value. And then this scalar operation here will be multiplied on every value in the ones array. So arrays can be combined with normal Python data types to do operations. And so you can do complex array operations using a mixture of arrays and Python data types. So you see here, you can quickly create an array consisting of only 42. Another way what you can do is you can create arrays that have a range of values. So there is a function called arange here, which stands for array range. It's similar to the Python range command, but it returns an array instead of a list. So if you run this here, you will get an array consisting from 0 to 9. And what you can do with this, if you want to create an array 10 by 10 with numbers going from 0 to 99, you can first create an array range with 0 to 99, and then you call reshape on that one to reshape it to 10 by 10. So then you get an array like that. So by combining these here, you can create the arrays you kind of any arrays you want. And also, all this operation doesn't reallocate anything. So the allocation of memory is done in the arange command here. That will create the array, the memory in memory. The reshape will only change the dimension, so it's just an interpretation of the data that you have created. And of course, you can give starting end values here, -10 to 10, the data type, of course. You can have a step length as well, just like before. So it's like the syntax is very similar to the normal range command. Yeah, you can specify the range here as well to get floating point values. It's also possible to create identity arrays. That is an array with ones at ones in the diagonal. Like this, we have ones here in the diagonal direction. And also, if you want to do, for example, plotting or linear ranges in Python, it's better to use arange is not the optimal way of doing that. So there is a special command to do this called linspace, and that will you give a starting point and an end point. And linspace will always guarantee that you have both 0 and 1 in the range that's created. And here you can specify how many values you want in that range as well. So in this case here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values, and 0 point is included and 1.0 is also included. So this command is very suitable when you want to do plotting later on, to create a range that you want to plot over. Then you use linspace to create this range. And here I have 20 values here in this last one here. You can do array expressions. So here I create an array here with 5 by 5. And if you use any of the operators in Python, so if you do an addition operator, by default, that is an element-wise addition. So it will take number 3 and add that to every element in A. If you do multiplication, same way, it will multiply every element with 3. Another nice thing is also that every mathematical function is also available in an array form. So in this case here, if I call np.sin, it will calculate the sinus value of each of the values inside A. I think you will recognize this is similar what you do in MATLAB. If you do negation, a minus sign before an array, it will negate the array. And you can also use plus to do element-wise addition of 2 arrays. Something a bit odd is that the array size, it doesn't have to be the same. You can add different sizes together, and the operation, the smaller one, will be repeated on a larger array. So matrix multiplication. So matrix multiplication, so the array data type in itself doesn't know anything about matrix, linear algebra and matrices. So if you want to do matrix multiplication, it's not the same as doing matrix using the normal multiplication operator. That is element-wise multiplication. If you want to do matrix multiplication, there is a special operator and function you can use. So in this case here, I have a 4x4 matrix or array, and the first thing you can do is you can do a.a. That will be a matrix multiplication, but you can also use the @ operator to do matrix multiplication. So these 2 lines are equivalent. Another thing you can do with arrays is you can do slices and subarrays. So indexing arrays is you use the brackets, and you can access. You can do multiple ways of accessing. You can do B will get the entire array, of course, but we12 will get row number 2 and column number 3. So compared to MATLAB, accessing array elements is done with a 0-based index. So every row starts at 0, 1, 2, 3. Compared to MATLAB, we start at 1, 2, and 3. So that is something different. So this statement here is actually print the row number 2 and column number 3 if you're in matrix notation. So that's a bit different. You can assign values to an array in the same way as you do print them out. So if you do A2 equals to 42, it will assign position number 3 in the array A with 42. Same thing here, position number 2, 3 in B. You can see it assigned this value here, and it assigned this value here. And just like in MATLAB, it's possible to do index notation as well. So you can specify a start and end range here, and that is using the same syntax as we have with range. So it will go from start and end -1. And you can do start colon, it will do from start to the end. And then you can do colon end, that is values up until end -1. Colon is all values. So in this case here, I have A1 to 5, it starts on 1 and it goes all the way up, but not including the number 5. So that is 1, 2, 3, and 4. And that is the right one here. And also this with memory location. So I have an A here with 25 elements. I print it out. And you can see, you can access prints out the actual memory and also print out the data of that array. So if I do B equals to A range here, and I print out the memory of B again, we can see what happens here. So in this case here, first we have the memory location here 5072. That is the absolute memory location of the underlying allocated memory block. A.data will actually point to somewhere in that data block. So in this case, you get an hexadecimal here. So this is, and then we create B. So that is a range from 1 to 5. And you can see here that memory of it's bit offset, but it belongs to the same memory block here. So when you do this indexing, NumPy tries to avoid reallocating memory as much as possible. But you have the same effect here with both A and B will always refer to the same memory in memory. So modifying B will also modify A. So here you see that this is modified here with 42, and the same thing with B here. And here are some other range operations here. You can use all elements except the last, all elements except the last two, last element of A, you have elements for with a step of 2, all elements in reversed order. This is a good trick to know if you want to kind of get the order of an element of an array in a different order. Here's more. You can do the same thing with arrays. So here you have all rows, all columns, 0, 1, rows 0, 0 to 1, last row in B. So all these operations, of course, work on multidimensional arrays as well. And also, it's possible to mix lists and arrays in different ways. So here an example here, if I have a 2-dimensional array B and I want to assign row 2 some values, I can just assign a normal Python list to this row. So you don't have to create a special NumPy array to assign a certain row. You can just assign a list, and it will know how to do this. So you see here I assigned this one here, and then the column down here as well. Yes, so array methods. There are several methods that you can use on array objects that are built in, just like the method that we used on strings. There are built-in methods on arrays as well that you can use. For example, one good method is sum, which will actually sum the values of an array. And you can sum in different directions. So if by default, it will sum all the elements, but you can specify here a value here. Sum 0 will sum the columns and return an array with the sums. 1 here will sum the rows. Same thing here, you can also do products. So the product of the entire array here is specified like this. And the same thing, the product of columns and rows here as well. There is also a derivative of the array that is called a matrix. And matrix is a special form of array that has built-in linear algebra operations. So it's sometimes suitable more if you want to do complex matrix operations in a syntax that is similar to linear algebra expressions. So in this case, I have A, X, and Y, and I can do transpose by calling A.T. I can do a matrix multiply here using the normal multiplication operator. And I can do A.I, which is actually calculating the inverse of the matrix. So that is, I think they are kind of on the way of deprecating the matrix data type in NumPy now, but it's good to know that it exists. And if you want to do more complex operations, expressions, then the matrix data type can be good to know about. So finally, there is also needs to kind of be able to read and write these arrays to disk. And there are multiple ways of doing this. There is a special binary format called MPY and MPZ that is built into this. You can do text files with row by row, and you can also use direct reading and writing of binary files. So writing a NumPy file is very easy. You just do np.save, and then you specify a file name and the variable you want to write to disk. And you can do np.save y and save the variable to disk. So if you run this, you can see here that I have two files now, xnpy and ynpy. And you can see here that they are not very good at printing out. So those are written in binary format. In special for, you can see there is a header here called NumPy to describe it. So an efficient format, good if you want to do scratch arrays during calculation on the computer or HPC resource where you need to save the state. You can use this one as well. Reading them again is done using the load command. So x equals to mp load, y equals to mp load, and then you can do plotting, which will be done shortly later here. So this is a plot of the values I read from disk. It's also possible to use a normal file object to read and write. So in this case here, I open a file xy.dat, and I specify here WB because B stands for binary. I want to write a binary file, and I open it as a F object, and then I can, instead of specifying a file name as a first parameter, I can specify the file object. Then it will write down X and Y to the same file. So in this case here, both of them will be written to a single file xy.dat, and then I can load it in the same way again. I need to do read binary, and then load X and load Y. So it looks like we got the same values that we wrote, so that's good. You can also read and write text files. Now I download a file here called U, V, and W, which contains data that in table format. So the data in that file looks something like this. So that could be some scientific measurement data, and we want to read it into NumPy. And what we don't want to have is these things here. So we would like to skip these rows in some way to go to the data here directly. And there is a method called load text, and you specify the format here. And then there is an option here called skip row, and that will skip the first two lines and then starting to read the data. So let's see here. So now you see here that it just read a file that consisted of 299,520 values and 6 columns. That's why it took a bit long to read it here. And you can see also the first numbers here is 0 and -1. Yeah, it seems to be correct here. So it read all these data and stored it in an array. And using these commands is actually a lot faster than using normal reading line by line. So if you can, use the built-in function in NumPy to read data, because these are implemented in C and really fast. Same thing here you can do. In this case, I do text array here, random values, and save them to disk. And you see here the file that has been written. Same thing here. And you can specify the delimiters between the numbers. You can also specify the formatting. And you can specify a lot more. In this case, I can write a header file and a footer to the file. It's also possible to write binary data. So now I'm going to download a binary file. It's actually a PNG file. And I will read that into an array using image IO. And you can see here I wrote, it read this file here, and it's 359 by 500 by 3 array. So this most image now an array. And then I can use read that again and write that to a file. And now it's a raw file, and then I can import this one here. So this is a raw image binary file, and to read binary files from Numpy, you need to specify the data type because it doesn't know from the file itself what kind of data is stored in it. So in this case, I know that every data point is stored as a unsigned integer of 8. And then I read that into file, and then I get my data array that is this one-dimensional array. And then I can reshape that into the size that it had before. Whoops, there is an image of something. So you can read binary files as well. As long as you know the data types, you can read and write binary files as well. I think I skipped that one, but we go to solve equation system as well. So if you need to solve a system of equations, there is a built-in solver called linalg solve that you can use that we can solve equation systems as well. There's a lot of built-in functions, and the same thing here. Look into the documentation of Numpy to see what functions are available. There's a lot of them. So let's see. Next step is final part is plotting, and I will. So the final part here is how you get your data that you have created, your arrays, and to plot them in different ways. So there is some links here to the Matplotlib library, which is the most commonly used plotting library in Python. It can plot to multiple different formats. You can save it to disk. You can open it in different window manager. You can open it in a notebook. So usually what you do is you don't want the big Matplotlib module. You want to have the Matplotlib pyplot module. So pyplot is a simplified plotting module that has the same syntax as you have in MATLAB for plotting, and you import it as PLT. This stuff is just for notebook that it produces the plots in the right way in my notebook. So the easiest way to plot is just to call the plot command and just specify the values as a list or an array. And then you do plot show here. For notebooks, it's not strictly necessary to do the show. I need to import that as well. And then it prints out or draws a diagram like this. So if you run this standalone using a spider, it can show it as a. So if you execute a Matplotlib program, it will display a window if you're not running from inside a notebook or a spider. Otherwise, it will in Spider it will use a special plotting window at the top to show the plots. So Matplotlib tries to adapt to the environment it is running in. So it can handle NumPy arrays as well. So as I said before, to plot a range of values here, you can use linspace here to define the range. So in this case, I go from 0 to 2 pi, and I want 50 values, and then I want y to be np.sin. So what actually happens here is, it looks kind of simple, but the first line creates an array of values, a range of values, and then y is actually, it computes a sign of each of these values in that array. So if you print this out, you will see here you get two arrays with one with x values and one with y values. And we can take both of them to plot them both. And now you see you get a nice sinus function plotted. You can change the line types to be plotted using additional parameters here. These are actually the same kind of parameters you use for MATLAB plotting here. So,
excuse me.
Yeah.
With the line space, so 2 pi is not the last element, right?
It guarantees you to get this one here is included in the array.
It is included in the array.
Yes.
But the y is not 0 for the last element.
That is probably due to a numerical.
Okay.
Yeah.
Okay,
so
but the beginning
0.
and the end are both included in the line space.
Yes.
Okay.
Because I think range and a range or whatever, they don't include the last one. Is that right?
No, they don't include the last one, and especially a bit problematic if you're using the step parameter in the a range as well. So that's why if you want this functionality with, you want to start value and an end value that is included, linspace is better to do that. And you can also calculate the values in between automatically, so you don't have to do that yourself. Okay, so you can change the appearance of the plots as well using, so this is red, and I want rounded markers on the plot. And I see here you get red circles here. I can do blue line. I want red dots, and I want them to be, there should be a line between them. So dash will be a line. You see here with blue dots with a line between them. And then you can do dash line as well using double dashes here. And you get a blue line with dashes like this. And you can do plus signs as well. And a combination of that. So this is kind of really quick way of plotting things in Numpy, and also in when you're doing things with your code. So it's a very easy interface to use. Then you can do a lot more. So you can do the assignments I leave because I have a bit short of time here. You can also do multiple series in the same plot. So in this case here, I have I create linspace X, and I create Y1 and Y2, so 2 plots. And then I can specify the first plot here by the first 3 parameters, and then I just add another 3 parameters for the second plot. And then you will get the same, both of them in the same diagram. You can change other properties by listing. There is if you documentation for plot, there is a lot of different parameters you can specify, and you can specify here line width, for example. Then it will be plot with a bit thicker lines. You can also, when you do plotting, it can return you 2 plot objects for each of these. For this one, it will return line 1, and for this one, it will return line 2. And then you can separately set the line width for each of these plots here. So then you use line 1 to set line width 4, and we set line width 8 to the second one here. You can also do return lines here. It will be a list of the different lines that they plot, and then you can use this to set properties on all of them at the same time using the setp command. You can also do multiple windows. It's a bit different when you do notebooks, then it will basically be 2 plots on top of each other. So you create a new plot by specifying figure, and then you can specify a number. And then you can specify another figure with a different number. Then these are 2 unique plots. And then they will be plotted on top of each other like this. If you're running this using standalone Python interpreter, you will get 2 windows for this. It's also possible to have a subplots. You can divide a single window into several plots. And this is a really odd way of specifying things. So you can do subplot here, and then you specify an integer number with where the first number is the number of rows, and the second one is number of columns, and then the first plot. So 2 rows, 1 column, and the third number is the actual plot itself, so number 2. So this is plot with 2 rows, 1 column, and this is plot number 2. It's a bit odd, but then you get them same. Divide as a plot up in 2. And if you run this standalone again, you will get a single window with 2 plots in the single window. So figures will produce separate windows. Subplots will be same window but multiple plots in them. And you can do it the other way around. You can have 2 columns instead. Then you get this output instead. You can also decorate plots in multiple ways. So you can specify using X label, the label of the X-axis, Y label, the label of the Y-axis. And it looks like this. Now you have y2, y1, and then you have x here.
Do you hear
Because
me?
yeah.
Excuse me, just wanted to ask if for the subplots we also define the coordinates of the plots, not only the number of rows and columns, but if where we want to have that subplot. Is there any way to define that, to specify?
And you mean where the window should appear?
No, for example, now we have the first the red curve to the left and the blue curve to the right, for example. And if we want to have, for example, one smaller and one bigger, and we change the order, or maybe it's not so clear when we have only two, but when we have more, for example, one big one, and there are like several smaller ones, but they are all in one plot. Do we need to also specify the coordinate of the
I think that it should be possible to have 2 by 2, and then you have to specify, I think, an additional number here. But I think you have to check the syntax of this. But I know that you can have 4 plots in a single window and more, and then you have to probably specify 1 1 1 2 2 1 and 2 2 as a fourth parameter here somehow.
Okay.
Yeah. But sometimes it's better. Yeah, it depends on what you do. But you can. I'm almost 100% certain that you can do this, but I'm not. I haven't done it myself here. So, but check the syntax of the subplot command, I would say. Then you can also, let's see here where we are. You can do a lot of other things. So you can actually add more text into the plot as well. So using the text command here, and that takes a coordinate here in the plot coordinate system. So you specify the coordinates in the same coordinate system as your plot itself. So here I do mp.pi.2 and 0.8, and then I can actually specify a latex function inside so that it will actually plot as a math equation, and you can center the alignment here as well. So now you see it plotted the equation in the plot as well here. You can also do annotations, so you can point at something in the plot. So annotate will kind of create an arrow pointing to something in the plot. So in this case, it says max here, and you can specify the starting point, where the text should be, properties of the arrow here, black, and the different properties. You can look at the documentation here. But now it plots an arrow here. It's also possible to specify where you want to look at the plot. So you can do the axis xlim and ylim to kind of specify where you want to zoom in. So now we zoom into this upper part of the plot, and the arrow is still pointing at the same position. You can also change the scales here using the X scale here to logarithmic here, and so on. So it's very powerful, and I will just show you some examples of other plots here. So histograms is what it sounds like. You can plot histogram values. Also, the homepage of Matplotlib has a lot of examples on the front page on how to plot. So usually, if you see a plot there, this is a plot I want, just go into that and click on it, and it will show you the code for that plot, and then you just modify it for your own needs. You could do bar charts. It's very simple. Bar X and Y. You can do scatter plots. Like this. Here's also a grid option here. You can switch on to show the grid. A legend as well here, because we have several data points here. It can add a legend in the plot as well. You can do contour plots. So here I have, you create 2 linspaces here for the -6 to 6, and how many values you want, and then you can put them together in something called a mesh grid, which you can use to calculate the values in each grid point using this expression here. So Z equals to mpsin X and Y, and then you plot X, Y, and Z, and you can get something like this. You can, of course, also display images. So in this case here, I actually download an image from the web. And then I can use plot imRead to read the image, and then I can do imShow to show the image like this. And you can also change how to interpolate the pixels that you have read in images here. There are multiple different filters that you can apply to the plotting as well of images. This is something I found on this web page here. So you can see different kind of filters you can apply on the image display. Streamlines can also be plotted. Marshall, I already showed that one. Okay, so yeah, this is also something you can plot. This kind of plots. And of course, it can do 3D as well. So it has a mplot 3D toolkit that you can use to plot values as well. And then you get plots like this. So this was a very short introduction to Matplotlib. But as I said, if I go back here, if you look at, there is a lot of good documentation here on the Matplotlib page here. And all of the commands that you can use are available here. And most of them are also, there are examples you can use. And if you go to the examples page on Matplotlib, here is very nice overview of the different diagrams you can plot. And if you, okay, this is something I want to do, I click on that, and there is a complete source code for how to implement that plot. So, and I think this is really a nice way of, you probably have an idea on what you want to plot, and then you can go into this and kind of look through here. Oh, this looks something like something I want to do. And then you can go into this and just look at the code and modify it. And there is a lot of examples. Matplotlib is also possible to integrate. I will show this later on when we do user interfaces. You can actually integrate Matplotlib plotting inside a user interface application as well. So you can create really nice applications with user interfaces and integrated plots and take advantage of all the functionality as part of Matplotlib. So that was all for today. Any final questions? Otherwise, I will stop the recording now.